Okay guys, I wanted to do another relatively short video here. This one goes into a little bit more detail, at least conceptually, um, about the idea of the shielding constants that we talked about in the last video. So recall that um, the value of sigma here, the larger it is, the smaller the magnetic field at a given nucleus within an atom. And so the larger the value of sigma, the more shielded the atom is. And we can think about the shielding constant as coming from three distinct terms. So there's a local contribution to the shielding constant that is due to the electrons within the atom that contains the nucleus circulating around and inducing a magnetic field on that nucleus. So the local contribution comes from the same atom that containing the nucleus that you're interested in. There's a second contribution coming from neighboring atoms. So let's say you have a nucleus of interest, and then there are neighboring atoms. The magnetic field, the external magnetic field, causes electrons within those neighboring atoms to circulate. That also can cause shielding or deshielding on the nuclei of interest. And similarly, depending on the interactions between the molecule of interest and its nuclei and whatever solvent is present, the solvent can have an effect as well on the magnetic fields that are local to that nuclei of interest. So you've got a lot of different things going into this shielding constant. We're going to start by talking about the local contribution, which is divided into two parts, the so-called diamagnetic contribution and the paramagnetic contribution. We'll talk about the diamagnetic contribution first. The sigma d values are positive, and so here the induced magnetic fields on the atom on the nucleus due to the electrons within its atom circulating, these oppose the applied magnetic field. Okay, so these are responsible for shielding the nucleus. The electron currents that we're talking about here are due to essentially the core electrons of the atom. That is, electrons that are very close to the nucleus and that consist of closed electronic shells. And so these electrons, when they start moving due to the external field, they move in such a way that the magnetic field that they create opposes the external magnetic field. And you can calculate the sigma d contribution using the so-called Lamb formula, which takes into account the electron density that's very close to the nucleus. And so here what we have some constants out in front, and then we have an expectation value. This is an electron operator that we're taking the expectation value of, and we'll take a look at a sample problem in a couple of slides. Before we get to that, there's another factor that affects the local sigma value, this diamagnetic contribution, and that has to do with whether or not the atom is attached to an electronegative atom. So if this nucleus of interest has a neighbor that is very electronegative, that we've already talked about this, that electronegative atom will pull electron density away from the nuclei of interest, and that's going to lessen the effect of the shielding. And so here's a diagram that describes it. Now there is an error in this diagram. So we're looking at this. You have a halogen, so this is a ethylene or an ethane molecule with a halogen attached to it, and so we're looking at these two different groups. So one the methyl group, and then the other the methylene group. In this figure, they've actually got the labels backwards, and so in my is that the case actually? No, I'm wrong. That's not correct. This is correct. right, you would expect that these guys here, the methylene hydrogens, which are attached to a carbon that is very close to the electronegative atom, you would expect those to be more deshielded compared to the methyl groups, and that's what you see here. And what it's illustrating is, as you increase the electronegativity of that halogen, the chemical shift increases significantly. Interestingly, for the methyl group, you get the opposite trend, and as Atkins points out, this is just to show that chemical shifts and shielding constants are very subtle creatures, and so you get an unexpected result here for the methyl group. Although this one does follow the trend that you would expect, that the more electron withdrawing this atom X is, the more deshielded these protons are, and so the larger the chemical shift that you see. Well, in this example problem, you're being asked to calculate the sigma d value using the Lamb formula. Okay, and so you need to evaluate this expectation value here, and so we want to think back to when we studied electrons and their different expectation values. So we'll just consider a free proton, and we know what the electronic states are for a free proton. And so what I've set up here is the expectation value for a 1s orbital, the expectation value of the 1 over r operator. So you have this would be the wave function squared divided by r. This is the volume element for the hydrogen atom, and if you plug in this wave function and do the integral, you would get this value for the expectation value, which you plug in here, and then you can calculate the value for sigma d. Okay. The other contributing factor to the local shielding constant is the paramagnetic contribution. Right? What we looked at just now was the diamagnetic contribution. The paramagnetic contribution still does involve circulating electrons on the same atom. However, for the paramagnetic contribution, what you find is that the shielding constant is negative, which means that the magnetic field that's generated locally on the nucleus actually reinforces the applied electric field. Right? Previously, when we talked about the diamagnetic contribution, that involves a positive sigma d that opposes the applied magnetic field. The negative sigma p value reinforces the applied, this should say, magnetic field, not electric field. The reason it's different is because the paramagnetic contribution involves electronic currents through unoccupied electron orbitals, essentially involving the excited electronic states of the atom. That's how it's different than the diamagnetic contribution, and this results in a deshielding of the nucleus. And it's a larger effect for molecules that have low-lying excited electronic states, where the electrons can easily reach the unoccupied molecular orbitals. We'll move on to the next contributing factor to sigma. This slide deals with the neighbor contribution. And so what can happen here? You have the nuclei of interest, and then it's connected nearby. There's a neighbor where electrons within that atom on that neighbor will start circulating due to the applied magnetic field. Now, when the electrons within that neighboring atom start to circulate, what will happen is that those electrons will then generate a magnetic moment on the neighboring atom. Okay, and so the strength of that induced magnetic moment is proportional to the external magnetic field, and the proportionality factor is what's called the magnetic susceptibility of the neighboring atom. And so that induced magnetic moment will in turn generate a local magnetic field on the nuclei of interest. And that induced magnetic field is related to the strength of the induced magnetic moment on the neighboring atom, and it's also related to the orientation of that magnetic moment relative to the nuclei of interest. And so that's depicted here in this figure. So this would be the neighboring atom, where the external magnetic field induces a magnetic moment on the atom. That is going to in turn create a magnetic field at some point here, which is a distance r and at some angle theta relative to that magnetic moment. And you see that there is a 1 over r cubed, so the farther away the neighbor is, the smaller the magnetic field, but then there's going to be an interesting angular dependence to that magnetic field, and that's depicted in this figure right here. So, so here you've got a little magnetic moment, and then what you're looking at here, these contours, these surfaces, these are different strengths of the induced magnetic field. And so the closer you are to the dipole or to the magnetic moment, the larger the field strength. So we have the darker blue representing a larger field, and then the lighter gray representing a weaker field. And then you see that the value, the magnitude of the field, I should say its sign, the sign of the field, depends upon the angle that you make with the magnetic moment. Okay, so it's complicated. Basically, is the point here. You have to take into account the different orientations of the molecule relative to the external magnetic field. And in order for this neighbor contribution to survive, it turns out that the magnetic susceptibility must be so-called anisotropic. This is very similar to what we discussed when we looked at microwave Raman spectroscopy. But in any case here, so there's a parallel magnetic susceptibility and a perpendicular magnetic susceptibility. So this refers to when you apply a magnetic field, to the molecule, what you need is you need the electrons to circulate differently depending on whether the magnetic field is oriented this way compared to oriented that way. If it's symmetric, that is, if the electrons circulate in the same way, no matter what the orientation of the magnetic field, then that would be an isotropic magnetic susceptibility, and you're not going to have a neighbor effect if that's the case. However, if there's a difference between having the field oriented in that direction versus having it oriented in that direction, then this induced magnetic moment will survive, and it will give you a contribution to the shielding. It's very interesting to look at aromatic rings. They have some of the more interesting features, and so here's this is the angular dependence that we discussed a little bit ago. Here's an aromatic ring. Okay, so what happens in the aromatic ring is that the pi electrons start making a circle here in the external magnetic field, and that gives rise to a local field, an induced magnetic field that circulates, or that that goes in this fashion. And so what you'll have is different directions. So the magnetic field is pointed in this direction for the protons that are in the plane of the ring, but for protons that are in these substituents above or below the ring, then the magnetic field points in a different direction. And so you wind up with the aromatic hydrogens being de-shielded because there's one sign for the magnetic field, but then the protons of the substituents are actually shielded because the magnetic field points in a different direction. So there's all sorts of interesting effects, magnetic effects that occur in molecules when you put them in a magnetic field. In any case, that's the neighbor contribution to the shielding constant. The last contribution that we'll just talk about briefly is the contribution due to the solvent. Okay, so typically your NMR sample is in a solvent, and depending upon the intermolecular interactions between your molecule of interest and the solvent, you may find that that the solvent can influence the magnetic fields on the nucleus that you're interested in. So if there's a hydrogen bond that's formed, or if there's some sort of complex being formed between the solvent and your molecule of interest, these can have a strong impact on the magnetic field, and then in turn it will affect the NMR frequencies for the resonances that you observe. And so one aspect of this is that the solvent has its own magnetic susceptibility. And so electrons within the solvent molecules are going to start circulating, and this will create an induced magnetic dipole moment on the solvent, which will then create a magnetic field that acts on a nearby molecule of interest. And so that's very similar to the neighbor effect that we discussed. Let's see, this one. Oh, and then, it's highly dependent upon the orientation of the solute in the solvent. So depending upon how the solvent actually solvates the molecule of interest, that will have an effect on whether there's shielding or deshielding effects present. And so here's an example. Let's suppose that you're interested in methane here. In a benzene solvent, that ring current that we talked about will have a strong influence on the methane, and the orientation will make a difference. It'll depend upon where that methane is relative to the ring of the benzene solvent. Well, I'm going to go ahead and stop this video right here.